So in today's class, what we will look at is the practical or the lab scenario for OSPF that we saw yesterday. Okay. So till now, what we have discussed is we were discussing there are three types of OSPF interfaces, not three types of OSPF interfaces. OSPF works on the interfaces, and the interfaces that it mainly works are of three types. One is the serial interface. Yeah, one is the serial interface, then the other is Ethernet interface, then the last one is loopback. This is what we saw. So, and we started discussing about the OSPF states based on serial interface. Now, please remember that. Now, please remember that these OSPF states, the configuration of the configuration of the OSPF with router OSPF one network ID, etc., and the purpose of this network and the wildcard mask combination of advertising the network and dynamic discovery of neighbors is true for all the interfaces. It can be a serial interface, it can be a Ethernet interface, or it can be a loopback IP interface. Right? This particular configuration and the purpose of the network command stays true for all the interfaces. Right? Where is the difference? Today we'll see that difference. Okay. When we do the practical, I'll show you that difference. So here we have two routers R1 and R2. The IP address on R1's interface is 12.0.0.1 and R2's IP interface is 12.0.0.2. We will create two loopback addresses on R1 and R2, 1111, 1112 on R1 and 22221 and 22222 on R2. Okay, so this is the basic simple topology. Now, okay. Now let me quickly just check. Show IP interface brief. IPs are already created. Okay. Okay. Over here, the thing is to basically save my time. I usually save the IP addresses and the OSPF configuration already. Okay. So that when I'm taking class for advanced level, I don't have to configure them. And the people who have enrolled for the advanced level, they already know about this. Right. So what I will do is I will remove all the pre-existing configurations and then we'll start again. So give me just 5 more minutes and we can start this. Okay, so now I have removed all the configurations, pre-existing configurations, and the two routers are the two routers do not have any OSPF or loopback or interface configurations as such. Right. So on let's first of all let's configure the IP addresses on each of these routers. All right. So configuration terminal interface serial 4/0 IP address is 12.0.0.1 255.0.0.0 and a no shut. All right. Then we will configure two loopback addresses as well. Okay, we will configure two loopback addresses as well. Okay. So interface loopback 1 IP address 1.1.1.1 255.255.255.255. Okay. Then interface loopback 2 as well. IP address 1.1.1.2 255.255.255.250. All right. Then and now let's go on R2 and configure these IP addresses. Configuration terminal interface serial 4/0 IP address 12.0.0.2 255.0.0.0 no shut, then interface loopback 1 IP address 2.2.2.1 255.255.255.255. Then interface loopback 2 IP address 2.2.2.2 255.255.255.255. So the loopback addresses have a address mask of /32 or 255.255, and the interface IP addresses have a address mask of 255.0.0.0 or /8. All right. So this is the subnet configurations. All right. Okay. Now to again, we know that to check the IP address configuration, what we do, show IP interface brief, and we can see the IP addresses. Okay. Now what we want to do is we want to create OSPF between the two routers. We want to create OSPF between the two routers. So let me first start the capture over here. Okay. And okay, let me also start the debug of these routers. Now, what is a debug? I used a new word called as debug. Okay. Debug means, okay, debug means to basically uh, note down, the router basically note down whatever is happening on it. Okay, it basically note down everything in the background, but it does not show us on the CLI. Okay, in the back of its head, okay, in the background, the whatever is happening on the router, it is basically noting down, or it is keeping like, you know, a note of it or a ledger of it. Okay, if you know, in accountancy we call it as ledger, right? So it is basically keeping a note of everything, okay, in the background. But when you debug, when you write the command debug, it basically means whatever is happening or whatever it is noting down in the background, it will show us on the CLI as well. Okay, it will show us on the CLI as well. So here what I'm doing is I'm debugging, or I'm telling the router to debug OSPF processes, so that whatever OSPF process happens, it will show us on the CLI. That is what debug means. So I will write few debug commands. Do not worry if you do not understand these debug commands. And honestly, these are not important from exam point of view. Okay, it's just for an understanding sake. Okay, debug IP OSPF hello. Okay. Debug with adjacency, debug IP OSPF events, debug IP OSPF hello adjacency events, and okay. So here what I did, whatever hello messages or whatever state changes, whatever OSPF packets that are exchanged between R1 and R2, it will show us on the CLI. I will run the same debug command on R1 as well, or sorry, on R2 as well. Debug IP OSPF hello, debug IP OSPF adjacencies, debug IP OSPF events, debug IP OSPF packets. All right. Now let us start to configure OSPF on R1. Configuration terminal. Okay. Router OSPF and question mark. You can see the process ID. The process ID that you can have is from 1 to 65535. And if you remember our discussion on what a process ID is basically helping the router to create a memory space with a particular process number. And I'm saying the process number is going to be 1. Okay. So router OSPF 1. Then the network that I want to advertise. the network that I want to advertise. Okay, network 12.0.0.0 network. Okay, and the wildcard mask is 0.255.255.255. Okay, and area 0. As I said, we'll talk about area 0 later. Okay, what is area? We will talk about that area later. All right, but just remember that two routers, if they want to be an OSPF neighbors or OSPF adjacent, see, they want to form an OSPF adjacency, they should be in the same area. Okay, done. Now let's go on R2. Okay, but before we go on R2, let's see what are the things that has happened. It says that it is saying we can see some OSPF event. It says a network was configured with 12.0.0.0.0 network and the address mask is 255. So what is happening with the wildcard mask? With the wildcard mask, it is looking for an IP address which starts with 12 and it falls under this area. Okay, yes. Or you can think of this perspective. If you remember our first discussion of advertising a particular network through the network command. Okay, so over here, this is 12 network. Okay, so 12.0.0.0 and the wildcard mask is 0.255.255.255. Okay, so how does wildcard mask work? Wherever there is 0, check that number and ignore the rest of the octets. So what OSPF is doing? OSPF is basically checking for any interface that starts with the IP address 12. And there is only one interface on R1 that starts with 12, that is serial 4/0, which has an IP address of 12.0.0.1. And it starts with 12. Okay. Now 12. Okay. What it's doing is it is advertising. Okay. It is because 12 is only one octet. 12 is only one octet. That is also the first octet. And for a first octet number, we know that the address mask is 255.0.0.0. And that is what you see here. In the first, it says, okay, undebug all. Here, we can see when I configured this, it says network 12.0.0.0 with the address mask of this is advertised. It is advertised. Okay, so the first purpose that we discussed, that the network command is used to advertise a particular network through the network command and the wildcard mask combination. That happened right now. And you can see that in the debug command here as well. This particular network is basically advertised. And how it is advertised? It is advertised through this interface, because this interface has an IP address of 12.0.0.1. That is why through this interface, OSPF is sending, or OSPF is advertising this particular network. And how is it advertising? How is it advertising? And we discussed the second purpose, dynamic discovery of. Second purpose was dynamic discovery, correct? Second purpose was dynamic discovery. And how is it discovering? Through OSPF hello messages, right? And we can see that here. Sending hello messages through this interface. It sends hello messages through this interface. And it sends the hello message at the multicast address of 224.0.0.5 from the IP address of 12.0.0.1. Okay, so here there are a lot of things that is happening. Let's try to understand this first. Okay. So here, what are the things that we can see in this debug command? What are the things that we can see in the debug command? Let's try to understand. We remember we had one discussion, or not, we discussed one thing, that OSPF is a layer 3 protocol and it sends it sends and it sends the OSPF messages at 224.0.0.5 and 224.0.0.6. Right. So that is what you can see here. It is sending OSPF hello messages at the multicast address of 224.0.0.5. That means the destination IP over here is 224.0.0.5. Okay. From the source interface 12.0.0.1. That means this is the source IP 12.0.0.1. Okay. So over here, what is actually happening? R1 is sending hello messages. Okay. It is sending a hello message. It is sending a hello message with the source IP as 12.0.0.1 and the destination IP as the multicast IP of 224.0.0.5. Now, what is this multicast? We did not discuss what a multicast means. Multicast means that, if you remember, we had a discussion on the types of traffic in layer 2. We discussed one as unicast, meaning it is a one-to-one communication. Then we know what is a broadcast. Okay, it is one-to-all communication. And then there is this multicast. What is multicast? Multicast is one to many. One to many. Many meaning or one to similar. I should write, there's not many. One to one to similar feature devices. One to similar feature devices. Okay, that is multicast. So over here, multicast is like okay, multicast is like, let's say, in a single room. Okay, in one room there are 100 people. Imagine, okay, imagine there are 100 people in a room. Okay, out of these 100 people, what is happening? 20 people speak Hindi. Okay, 20 people, they can speak English. They speak only English and understand English only. Okay, so 20 people can understand Hindi and speak Hindi only. Okay, it's not like they understand multiple languages. They understand only one language, that is Hindi. 20 people understand only English. 20 people understand only Tamil. Okay, 20 people understand, let's say, Marathi. Okay, and the next 20 people, for example, they understand only Malayalam. Okay, so in total, 100 people. Now, what is one-to-one communication? This Hindi speaking people can communicate with each other. One-to-one communication, right? What is one-to-all? If one of them sends a message, it will reach out to every people. Okay, that is what a broadcast was. Broadcast, it is for everyone. The broadcast message, but it's for everyone. Correct? That's what a broadcast. Now, what is a multicast? One to, as I said, one to similar feature devices. Over here, obviously, let's say one Hindi speaking person, okay, wants to share an information. What he will say, he will send information only, he will send information only to Hindi speaking people only. Correct. So the Hindi speaking people can understand Hindi, speak Hindi, write Hindi, read Hindi, etc. Okay. So whatever information he has, he will share it to his people, that is Hindi speaking people. Similarly, goes for English, Tamil, Marathi, and Malayalam. They will share information of their language to their people only. That is multicast. So over here, this multicast address of 224.0.0.5 is OSPF OSPF address. Okay, it is OSPF address. So here, what R1 is doing, R1 is sending OSPF hello messages at 224.0.0.5. It is OSPF speaking address. Any router who is enabled with OSPF will be sending messages at this IP address and will be listening to messages on this address only. Okay, will be listening and sending messages on this particular IP address only. 224.0.0.5. This is what a multicast OSPF multicast address is. You may ask this question: do every routing protocol have different multicast addresses? Yes, every routing protocol has different multicast addresses, and OSPF's multicast address is 224.0.0.5. Okay, so over here you can see the moment we gave network command, okay, it found out that serial 4/0 is the IP interface which starts with 12, which has an IP address that starts with 12. Okay, and the address mask over here is 255.0.0.0. So you can see it is advertising this particular network on serial 4/0. And on what it is advertising, how it is advertising this particular network to a hello message that is sent at the multicast address of 224.0.0.5. This is what we can see here. So 224.0.0.5 becomes a destination IP, and what is the source IP? That is 12.0.0.1. 12.0.0.1, which is basically serial 4/0's IP address. So there are so many things that we can understand through this debug command. Okay, now let's continue that debug. So you can see here at every 10 seconds of interval, we discussed yesterday that at every 10 seconds of interval, OSPF will send hello message, right? So you can see here 22.603. Okay, it's because it also involves microseconds. Okay, so you may not see exact 10 seconds of interval that we see. We will see it involves microseconds of as well. So 22.603 after 10 seconds, that is 31. Then 10 seconds 41. Then 10 seconds 50. 10 seconds 60. 10 seconds 10. 18. 10 seconds 27. 36. 45. So at every 10 seconds of interval, you can see OSPF is sending hello message. Okay, now it is sending hello messages. And we discussed yesterday what will be the contents inside the hello message, right? In the hello message, it will share about the address mask, the subnet mask, the hello timer, the dead timer, the area that it belongs to. All those information will be shared, and also the router ID. Router ID will also be shared. Correct. So let me to check the information present inside the hello messages. I am opening Wireshark. All right. So you can see it is continuously sending OSPF hello message. All right. Now you can see hello message is sent. You can see it is a hello packet. OSPF hello packet. Who is the source IP? 12.0.0.1. That is router's IP address. Router 1's IP address. And it is sending this hello message at a destination IP of 224.0.0.5, which is the multicast IP address for OSPF. Okay. Now let's open the OSPF messages. OSPF hello packet. What are the information present? Okay, you can see the router ID, OSPF router ID, that is 1.1.1.2. And we discussed yesterday how a router ID is chosen. How a router ID is chosen. Router ID is chosen based on the highest loopback interface. And if there is no loopback present, then the highest IP interface will be chosen as the loopback address. And on R1, we have two loopback interfaces, 1.1.1.1 and 1.1.1.2. Obviously, 1.2 is a higher loopback interface, and hence this is chosen as the router ID. Okay, so this is, you can see, source OSPF router ID 1.1.1.2. It is the router ID. Okay, then what are the other information that is sent? Subnet mask and the address mask is also sent. Okay, so you can see here network mask 255.0.0.0. That is the address mask. Okay, address mask that is sent, right? Then I also mentioned it will also send the hello timer and the dead timer information. So you can see here, yeah, hello interval that is 10 seconds and dead interval that is 40 seconds. That is also sent, right? And they should match. Okay, your hello timer, dead timer, your area, your subnet masks, your address masks, they should match. Okay, so now what has happened here? We have configured OSPF only on R1. Let us configure on R2. But for understanding sake, let us try to have a mismatch. Okay, let us try to have a mismatch. So what are those mismatches? We know that the router ID should not be same. Okay, let us try to make the router ID same on R2. Then subnet ID or the address mask of the neighbor should be same. Let us try to create a different subnet mask. Okay, then the hello messages, not the hello message, the hello timer and that timer, it should match. Let us try to make possible that they should not match. Okay, and let's see what will happen. And the area should match. These are the few criteria for the hello messages to be exchanged and move forward. Now let me first create OSPF on R2 and let's keep everything at its default site. So configuration terminal, router OSPF 1, okay, network 12.0.0.0, 0.255.255.255, okay, area 0. Okay, so you can see there are so many things that is happening in the background. Okay, now undebug all. There's so many things that has happened in the background. Now you can see here, let us go back to our understanding of things. We configured OSPF on R1, then we configured OSPF on R2. We know that the moment we configure OSPF on R1 and R2, they will send hello messages to each other. And in those hello messages, what are the information that is sent? The router ID, okay, subnet mask, okay, hello timer, dead timer, okay, hello timer, dead timer, and the area. These are the few important parameters that are sent in the hello message. And what are the parameters that should match? The subnet mask should match, hello timer, dead timer should match, and the area should match. Router ID should not match. Okay, let's check from that perspective. So on R2, the moment we configured network, the moment we configured OSPF and advertised this particular network, you can see serial 4/0 has gone up, and it is also sending hello message on this particular IP address from this source IP.
So this
All right.
12.0.0 network is the connected one or the other side? 12.0.0.0 network, that is which is connected between the two routers, that one only.
Yes. Yes.
So that one, why they need to advertise? They already know that it is connected one.
Yes. You're absolutely right. Okay. So I don't have to see if I really don't have to advertise this particular network, but for understanding purpose, I advertise it. Give me a minute. Give me a minute.
Okay.
Vedansh. So there was no need for me to advertise 12 network because they're directly connected. Okay. But as I said, for understanding purpose of how OSPF is working, how OSPF is advertising those network, I gave that example. Okay. And from what you said is absolutely right. And from that perspective, there was no need for R1 to advertise this network because they're directly connected, right? But however, as I said, for an understanding purpose, I advertised 12 network. So if you see here, show IP route, okay, you can see 12 network. You will see it is directly connected. You will see it is directly connected. All right. Now, because you have asked this, if any network is learned through OSPF, in front of it, there will be O. O meaning OSPF. C over here means connected. It is directly connected. Okay. So as I said, for understanding purpose only, I advertise the 12 network. Okay. Now, not OSPF, R2 is also sending hello messages from this particular interface. And when it's sent those messages in the hello messages, what are the information it is sending? Let's check that through the Wireshark. So you can see here, till here, R1 was sending the OSPF hello messages. R2 also sent the OSPF hello message. And on R2's side, what are the information present? R2's router ID 2.2.2.2. We have configured two loopback addresses 2.2.2.1 and 2.2.2.2. Obviously, 2.2.2.2 is a higher loopback address and hence it is the router ID. And if there were no loopback addresses present, if I hadn't created loopback 1 and loopback 2 on R2, obviously the serial interface IP address, that is 12002 of R2, would be the router ID. Okay. It also belongs to area 0, right? The network mask 255, that is also same. Then the hello interval is 10 and dead interval is also 40. This same kind of match parameters we will see on 12 or on R1's hello message as well. The router ID should not match. We just saw. This is R1's. This is R1's router ID. This is not a router ID. This is R1's hello message and this is R2's hello message. Okay. We can see everything is matching except the router ID and the checksum. We leave checksum as of now. Okay. You can see except the router ID and except the router ID, everything else is matching. Right. So this is what happens for the two routers to exchange hello messages. These parameters should match. Then only they will move ahead. Okay.
So now if I remove that loopback, what will happen? The router ID will change, or the 2.2.2.2 and this one, that loopbacks, if we remove both the loopbacks from R2, so what will happen?
Okay, let's see what will happen. Let's check that. Configuration terminal, no interface loopback 1 and no interface loopback 2. Your OSPF will basically fail first.
Oh, it will interface change administrator down, both change to down. Okay. There is no neighbor. 1112 it is there, no?
Okay. Now, what has happened here is that router ID is already chosen. The router ID is already chosen. Okay. Let's go on the Wireshark and check this real time. From R2, you will still see the router ID being published as 2.2.2.2. So once the router ID is chosen, with that router ID only, the communication is going to happen. Okay. So it's like, as I said, router ID is like what are we doing? We are using the loopback address or using the nickname. We are telling the router ID, choose loopback 2 as your nickname. Okay. and use this nickname for all your communication or for all your further communications. Okay. Now over here, what has happened? OSPF has formed with the router ID 2.2.2.2. Now, even if you remove the loopback addresses, the OSPF communication is happening using that router ID. For the changes to happen, I will have to restart this OSPF process on R2. This router ID is only as for namesake purpose. It is not helping the router to exchange the data. It is only for the namesake purpose that from this particular router ID, a data is coming. And moreover, the data or the router ID is supported by the source IP address also 12002. Correct? You can see here for 12002, from the source IP address of 12002, a hello message is coming, which has a router ID of 2.2.2.2. Now, even when you have removed the loopback address, you have completely removed the loopback address, OSPF has already chosen the loopback name. OSPF has chosen the loopback name. And until and unless you tell the other router or you tell from your side that there is no loopback address, the communication is only going to happen between the loop using the loopback address as the router. Okay, so in order to explain you this, it's like Alice and Bob. Okay, Alice and Bob. Alice's nickname was Alex and Bob's name was Bobby. Okay, this is what we had discussed. So this is their professional name and this is their nickname. Okay, all the communication between Alice and Bob was happening using their nicknames. Using their nicknames. Okay, but the entity is same. The entity is same. Okay, so over here, if Bob, if Bob chooses that he does not want, if Bob chooses that he does not want the nickname to be used, let him remove that nickname. But he has not informed Alice about it. Alice would still be sending information to Bobby. Alice would still be sending information to Bobby. And Bob and Bobby, being the same entity, they will still receive those information and will process it. If Bob wants that Alice use his official name, Bob has to publicly announce or Bob has to tell that use my professional name rather than my nickname. And here is what is happening. Okay, so router 1, okay, has a nickname of 2.2.2.2, but his official name is 12001. Okay, and R2 over here is on 2.2.2. 1.1.1.2. Here it's 2.2.2.2 and the official name is 12002. Okay. In the actual data, you can see the actual data is being sent using the professional name. But the hello messages are being sent or the hello messages uses the nicknames. Hello messages are using the nicknames. So over here, what has happened? I removed the nickname. I removed the nickname. However, whatever hello messages are being exchanged, they still address each other using the router ID or their nickname. R2 specifically has to tell R1 that I do not have a nickname. Start sending or I will start using my official IP address as the router ID. And for R2 to use this official ID as the router ID, it needs to restart this OSPF process. Once it restarts this OSPF process, the next time when R2 sends the hello message, the router ID will be 12002. Got it?
Got it, got it. Voice is audible, right?
Yes. Now, we just saw hello message has been exchanged. Hello messages are exchanged between the two routers. Okay. And now we also discussed the OSPF states in our previous session. Once the OSPF or the hello messages are exchanged and these parameters like the router ID, area, hello timer, and dead timer are matched, they move into the state called as two-way state. We discussed this in the last session. They move into the two-way state, thereby calling themselves as OSPF neighbors, right? And we can see that over here. Okay. Send hello messages. It is also receiving. This is R2. Okay, we are checking on R2. Okay, we are checking on R2. So R2 is sending hello messages out of this interface. It is receiving hello messages from R1 as well. So they exchange each other's hello messages. They checked their matching criteria, router ID, area, subnet mask, etc. All that thing they matched. And finally, when they matched, they went to a two-way state, two-way communication with 1.1.1.2. And state is two-way. State is two-way. Okay, state is two-way. So any of those parameters, okay, I can make those changes, but it will make this lab very lengthy. And for people who are just learning OSPF, it will be very, very confusing for them. So I'm not going into that level of detail, but this level of detail is important to understand how OSPF is basically working. Okay, and trust me, if if you're just a beginner or if you just have 1 or 2 years of experience, and even if you just simply explain them this amount of detail in an interview, especially from an interview's perspective, the interviewer will be extremely happy or impressed, right? So over here we can see the hello messages or the information present in the hello messages are exchanged. They are not negotiated, they are agreed upon, and the two routers, they move into the two-way state. They move into the two-way state, right? Now, once they move into the two-way state, the next state is, we discussed, it is an X start state. They move into an X start state. And in the X start state, what are the three parameters that are negotiated? Who will become the master and who will become the slave, right? Master is the router which has a higher router ID, correct? This is what we are discussing. So you can see here, it says, yeah, here you can see that it says preparing database exchange. Here it is preparing the exchange or preparing the exchange of database. And we discussed yesterday in the Xstart state, these three parameters are negotiated so that in the next state, the next exchange state, the DBDs are exchanged or your database descriptors are exchanged in the exchange state. So this message, preparing database exchange, everything is part of your Xstart state, is part of your Xstart state. All right. So you can clearly see here, it is mentioned Xstart state as well. So it is preparing, okay. 1.1.1.2 is preparing the database exchange. Okay. And what are the other information or what are the other parameters that are negotiated in the Xstart state? Who will become the master? Who will become the slave? Okay. Then what is the DVD sequence number and what is the MTU? These three parameters are exchanged, and we will see that over here. We can see DVD sequence number. This DVD sequence number is received from R1. Okay, but first let's go one by one. Who will become the master and who will become the slave, right? So over here, okay, you can see here, R2 clearly says, R2 clearly says, we are not the slave, we are the master. R2 clearly says, we are not the slave, we are the master. Why? Because R2's router ID is 2.2.2.2 and R1's router ID is 1.1.1.2, and hence R2 becomes the master. We are the master and we are not the slave. So the first parameter that is negotiated in the X start state, who will become the master and who will become the slave. We just saw R2 has become the master. Clear? Then the database descriptor sequence number or DBD sequence number. So here what is actually happening is R1 is also saying I am the master, R2 is also saying I am the master. They both say that I am the master, but R1 realizes that R2's router ID is higher and hence R2 should be the master. Right? So what is happening here is that R1 says that I am the master. Here R1 says that, yeah, R1 says that I am the master, and it has also sent the DBD sequence number. R1, okay, sorry, here R1 says that I am the master, and this is his sequence number. This is his sequence number, right? So, and when R1 receives R2's hello message, it sees that R2 obviously has a higher router ID, and hence the DBD sequence number should be used that is given by R2. That is given by R2. Let me show you that over here. Okay. So over here, you can see R1. This is R1's router ID 1.1.1.2. You can clearly see R1 is saying that R1 is saying that I am the master. You can see I am the master. Yes. And my DBD sequence number is 2889. This is what R1 is saying. Okay. Then R2 over here, R2 is saying I am also the master, and my sequence number is DBD sequence number is 2946. R1, R1 is also saying I am the master. R2 is also saying I am the master. Then R1 realizes that it is not the master because R2's router ID is higher. So over here you can see R1 immediately says I am not the master. Master? No, I am not the master. And what DBD sequence number is it using? 2946. 2946 was the DBD sequence number of R2. You can see here. R1's DBD sequence number was 2849. R2's DBD sequence was 29. R1 was 28 and R2 was 29. You can see in the next message, R1 agrees with, this is R1. R1 agrees with R2's DBD sequence. Okay. So this is what we have discussed. Also, the DBD sequence number of the master is taken into consideration in the X start state. Okay. So you can see here, after two-way state, your X start state or X start state is happening, where it is saying preparing of database is happened. Who is the master and who is the slave? That is also decided. We just saw how the DBD sequence number is chosen by the slave as well. The whatever DBD sequence number master is saying, that same DBD sequence number is chosen by the slave as well. And the last parameter was MTU. MTU is negotiated, or it is preferred to be same. You can see here 1500, 1500. The MTU is same. MTU is same. Okay, so MTU is also negotiated. Now, once all these parameters are negotiated, then the two routers move into the exchange state. They move into the exchange state where the two routers will exchange the DBDs. They will exchange the DBDs. So in our diagram, For R1, these are the connected links. For R2, these are the connected links. So this will be one DBD number 1 for R1, and this will be DBD number 2 for R1. This will be DBD number 1 for R1, this R2, this will be DBD number 2 for R2. Okay, so in the exchange state, the two routers are exchanging the information of the loopback addresses or the links that they are connected to with each other. Okay, so you can see here in the exchange state, you can see here it says received DVDs. Okay, send DVDs, send, etc. It is sending its own DVD. It is also receiving DVDs from R1. We are checking on R2. Please remember, we are checking on R2. Since R2 is the master, R2 is sending its own DVDs, and in response, it is receiving R1's DVDs as well. And we can see that over here. You can see DVD, etc. This is what is happening. R1 and R2 are exchanging the DVDs with each other. They are exchanging the DVDs with each other. All right. Then once they have exchanged the DVDs, they will move into a loading state where full exchange of database happens. So you can see here, after the exchange state, they are basically exchanging the database. And it says that from it, the OSPF process has moved to the from loading to full state. Basically, from exchange to loading, it does not show. This exchange, it means the two routers are exchanging DVDs as well as they have moved into the loading state as well. Once in the loading state, the full database has been exchanged with the between the two routers. The two routers move from loading to full state. And over here, we can see that. Here you can see that they are exchanging DVDs, and also now in the loading state, they are exchanging their whole database. And once the whole database is exchanged, the two routers move from loading to full state. Okay, so this is what happens when you create OSPF between the two routers. Okay, and now let's check when they have exchanged the database. That means R2 has shared the information of its connected links to R1, and R1 has shared the information or the database of its connected links to R2. So R2 should know about R1's loopback addresses, correct? Let's check. Show IP route. Okay, so over here, you will see R2 over here knows only about its own connected links. Similarly, R1 also knows about show IP route. It knows about its own connected links. R1 does not know about 2.2.2.2. R2 does not know about 1.1.1.2. Okay, now you may ask, we just understood that the two routers will exchange their whole database. Okay, but they have not exchanged. R2 does not know about R1's IP address, R1's loopback addresses. R1 does not know about R2's loopback address. So how am I saying that they have exchanged their whole database? Now let's go back to our understanding of how network is being advertised using the network command and wildcard mask. Let's go back to our understanding there. Okay, if you remember, our thing was advertise that particular network. Advertise the network. Over here, what we did, let's understand this particular network or this particular command to understand our scenario. The command over here is 10.1.13.0 network and 0.0.0.255. Okay, wherever there are 0, it will make a note of it and it will ignore the next. So over here on R1, this is the only interface. This is the only interface that starts with 10.1.13. And out of this interface only, the OSPF hello message is sent. Correct? OSPF hello message is sent. This is what we had discussed. OSPF hello message is sent. And over here, 10.1.13.0/24 network is advertised only to R3. Only to R3. None of the other networks, 12.1, 14.1, 2.1, 1.1, these networks are not known to R3. This is what we had discussed. Correct? Right? This is what we had discussed. So R3 only knows about 10.1.13. network. So if any data that comes for 10.1.12.1 network, R3 does not know about it because R1 did not mention. R1 has not advertised it using the network command. That is what is exactly happening here. The command that I used was network 12.0.0.0 0.255.255.255. Okay, so over here 12 and the rest of the octets were ignored. So the only interface that starts with 12 is this interface. And through this interface, OSPF message is sent. And 12.0.0.0/8 network is advertised. These IP addresses are not advertised. Why?
But if you do
Because
the
in the,
same thing, then it will go, right? If you do for 111
yes,
also with the
if I advertise network, these network, then OSPF message or OSPF ad will advertise these network to all the hello message.
but in that above image, so there also the same thing will happen. So in the above image, you showed that ABC router 1, 2, 3, 4 was there, 4 router image.
Yeah.
Here,
Right.
here that
Yeah.
this one, the 10, 10, 1, 12, 1, that network, if I show it towards router 3 also, then also it will go to router 3, that network, which is going to router 2, 10, 1, 1, 10, 1,
Give
12, 1.
which network command are you saying?
Above one, that G0 by 0. In that one is there 10.1.12.1/24. So that one, that network, if
Yeah.
I pass it through this, then it will go to R3. The same if I do that
As well.
expose it, then
So this one. So let's take consider this network command. Okay.
yeah.
10.1.0.0.0.255.250. Okay. So here 10.1. The other two octets are completely ignored. So, okay, to answer your question, I'm giving you a broader perspective. Okay. So over here, OSPF is going to check which are the interfaces which has an IP address starting with 10.1. Okay. This one, this one, this one, this one, and this one. So out of all these five interfaces, OSPF hello messages are sent. OSPF hello messages are sent out of these five interfaces, and out of these five interfaces, 10.1.0.0/16 network is advertised. Okay, 10.1.0.0/16 network is advertised. Why? Because this is 0 and 0. And with only two octets, we know that the address mask should be /16. Correct? Now on R2, 10.1. It will know about 10.1.12 network. It will know about 30 network. It will know about 40 network. It will also know about one network. It will also know about two network. Why? Because 10.1.0.0/16 covers 10.1.1.1, 10.1.2.1, 10.1.12.1, 13.1, and 14.1 network as well. Got it?
Okay, okay.
Okay. So in our diagram, in our network diagram, we advertised only, we use the network command 12.0.0.0.255.255.255, and hence only through this interface the network is advertised, and only this particular network is advertised. Okay, now let me give you another perspective. Let me also advertise those two IP addresses. Configuration terminal, router OSPF 1, okay, network 1.1.1.1, okay, because we have used the subnet mask or address mask as /32 0.0.0.0 area 0, okay, then 1.1.1.2 as well. Okay, so over here I am using this particular network command 10.1.13.1 0.0.0.0, that is 10.1.13.1. So I am choosing this exact IP address. Okay, I'm choosing this exact IP address. Okay, I'm choosing this exact IP address. All right. Now, as per our diagram, okay, those two exact IP addresses are these two IP addresses. And so what is happening is we have enabled IP, or we have enabled OSPF on loopback 1, on loopback 2, and the previous network command was with serial 4/0. So on these three interfaces, your OSPF is enabled. And on these three interfaces, all the networks, that we used or that we are choosing to advertise, they will be advertised through these OSPF interfaces as well. Loopback 1 interface will advertise loopback 2 IP and serial 4/0 IP as well. Loopback 2 interface will advertise loopback 2, loopback 1, and serial 4/0 IP as well. Serial 4/0 will advertise itself. It will also advertise loopback 1, and it will also advertise loopback 2 as well. Okay, to give you a proof, okay, serial 4/0, okay, when we advertised 1111 and 11112, serial 4/0 would have updated R2 with these two networks as well. Okay, so let me show you over here on R2's routing table. Show IP route. Now you will see 1111 and 1112 as well on R2's routing table. So it is not advertising just through this interface about this network. It is advertising not only this network but every other network where OSPF is enabled. Where OSPF is enabled, it is also advertising those networks as well through this interface. That is why over here R2 now knows about these two networks as well, or these two IP addresses as well. Clear?
Yes, got it.
Okay. So over here in this diagram, because the OSPF message was sent only through this interface. Okay, OSPF message was sent only through this interface, and only this particular IP address was being covered. That is why R3 would know only about this particular range of IP addresses, not any other IP address. Okay, if for some reason I choose a particular address mask which covers these two interfaces, okay, not for some reason, I configure a wildcard mask which chooses these two interfaces. So OSPF will be sent to these two interfaces, and these two interfaces will advertise about each other as well. So R2 over here, R2 will not only know about 10.1.12.1 network, it will also know about 13.1 network as well. Similarly, R3 would not only know about 13.1 network, it will also know about 12.1 network as well. Clear?
Yes, yes.
So with this, we'll stop our discussion for today's class and we'll continue tomorrow.